back. This is the UPTIME podcast. This is episode 6. I'm your co-host, Dan Blewett. And here on the UPTIME podcast, we talk about wind turbines, lightning protection, and everything renewable energy. I'm joined by my co-host, Alan Hall, lightning protection expert. Alan, how you doing?
Hey, great, Dan. How are you?
Doing well. Quarantine week, whatever. We don't even know anymore. Where are we? What day is it? Is it nighttime? Is it daytime? What's happening? It's raining outside, so can't go outside today. But how's your quarantine?
Everybody is just quiet. I had a phone call today, of all things, from someone I haven't talked to in quite a while, and he's got 3 younger kids. I asked him how it was going with having the kids home all the time. And he said, "Well, it's going."
Yeah. Yeah.
It's hard to explain it to younger children, and the older ones know more about what's happening and can kind of understand it. But the younger ones, I'm not sure if it's just kind of overwhelming pleasure of not being at school, or is it just complete total boredom. So they probably actually bounce from one edge to the other on the boredom to excited scale all day.
Yeah.
It's got to be hard.
Well, that's the thing with summer vacation as a kid. I mean, you're out of school and you're so excited and you have lots of stuff to do. But then when August rolls around and you're like running out of stuff to do and you're sitting at home and there's no baseball games and your friends are on vacation, you're like, I don't like school, but I kind of want to go back. And that's got to be everyone's constant state right now. I mean, there's only so much to do in your house, even though video games are, much more prevalent they were when I was a kid, at least.
Oh, and they probably making a killing right now, right? Video games have got to be hot. Online video games have got to be exploding, just like Netflix and Amazon and all those video services and Zoom, right? So that the online presence has got to be just huge right now, and good for them, I guess. At least they're there for us.
Yeah. Well, it's funny we were talking about, some of the future of travel and autonomous vehicles and how it'll allow us to travel so much faster. But at the same time, this quarantine has also really accelerated the technology of staying at home and doing stuff digitally and stop having so many meetings in person because they're superfluous. So you wonder if we're almost going in opposite directions. Like, yeah, we could take an autonomous aircraft in 5 years to get to a meeting really fast, but let's just do Zoom because why?
It's easier.
Yeah. So they're almost fighting each other. But
I kind of wonder that. I wonder because I've done a number of Zoom meetings. I had done a number of Zoom meetings before this happened, and obviously now I do them all on Zoom. We've been using Zoom as our platform, and it at least with Zoom, you kind of feel like just the way it's set up. It's simplistic. It's easy to use. You can get on it, get off it. So it's not a complex system. But it's funny because I thought that when we did online video conferencing a year ago, it was hold meeting over, everybody's off. Mm-hmm. Now it's kind of warm into meeting, talk about the stuff we would talk about if we were all there. Yeah. Have the meeting and then talk about the stuff we would have talked about in the hallway afterwards. In the Zoom call. So the Zooms have changed too. So you're get to know people again instead of just being just cut and dry, get on, get off. It's more social. Yeah,
it's
like Facebook.
Thing.
Yeah, no, it's not bad. We'll take it.
Yeah, I mean, do what you can in these trying times. It's funny. Everyone's like sarcastically saying these trying times. Like that's like something your grandma would say. Or your grandpa would say.
And they actually had trying times. We don't have trying times. If this is as bad as it gets, this is nothing to what my grandparents went through.
Yeah,
nothing.
I was watching the Ken Burns documentary, The Roosevelts, a little bit. I don't watch much TV at all. But my parents suggested it, and I'm interested in getting to know some of the old presidents.
Washington, D.C., you have to be interested, right?
Yeah, I do appreciate the history of where I live today. There's a little bit of pride there. And, so the Roosevelts thing was very cool. Obviously, FDR, was in charge during the Great Depression. And, yeah, it just gives you some perspective. I mean, a lot of people are going to be out of work. Like, there's a lot of very serious implications for our economy right now that are going to continue to get worse.
Yeah.
But when you go back in time and you look at the Great Depression, where 25% of people were unemployed, and they're lining up to, get food rations
to eat. Yeah,
very, very different. So, thankful that we're still in this version of, economic depression versus that.
Oh yeah, I think I'd take this over the Great Depression, no doubt, and I'd take it over any world war. That's for sure. Uh, it's been an inconvenience, and it's going to be a financial hit to everybody. I don't know who's going to come out this on the upside, but if this is as bad as it gets, then we're going to be okay.
Yeah, for sure. So today we're going to talk about a little bit of research on some blade testing, some scale stuff with blades. Also going to talk a bunch about different types of lightning and the implications on wind turbines. So let's talk a little bit about some of the footage. And so we were talking before the show started off camera about how you, back earlier in your career, for the first time saw some of these phenomenon that you only heard about, like step leaders. So
Yeah.
Tom Warner was the one who's kind of taken a lot of really slow motion video. Like, what do you say? Was it 103,000 frames per second?
100,000 frames per second. I believe that's what he's taking video in. Yeah.
Yeah. So talk a little bit about that and what we've learned from some of the slow motion video.
Well, because lightning happens so fast, and because it's so bright, it's very hard for the naked eye to actually see what's happening and to pick out some of the precursors to the big flash that we normally see. And getting high-speed video cameras digital cameras to record lightning strikes and some of the precursors to lightning and some of the electrical discharges that happen in the cloud before you see the lightning strike the ground or wherever it's going to strike, that was just not there. And Tom had done a good job of recording some of that, so you can actually see the propagation of the lightning channels through the sky. That, if you're working in aircraft and aircraft lightning protection, it's a big help to think of it that way, to actually see how it moves and understand in this high-speed video, the aircraft's not moving very far, but how things are propagating and how they're splitting in the case of negative discharge, cloud to ground, how the branching occurs in a positive cloud to ground, how there's just kind of one continuous channel that happens. And you see it in the lab, and I used to work at Lightning Technologies, and at Lightning Technologies, they have a very advanced high voltage lab. And so you do enough tests, you can actually start to see those. We used to photograph them with UV lenses, and so we can actually see some of the electrical discharges, a negative versus a positive, and see the differences in that. But to see it in the sky was really revolutionary. I always, and it wasn't just me that had noticed that. Most of the aerospace aircraft lightning protection people working at the time had seen it or had discussed it. And it was really, really helpful because it just took the book reading you had done and sort of the still photographs you had seen from the 1920s and 30s and put it into live action. So it's like seeing The Wizard of Oz for the first time in color versus any other movie that didn't have, it was black and white and it had no sound. It's just that kind of revolution happened right then. It's just mind-blowing. Mind-blowing.
Well, when you read about some of the stuff like step leaders, you're like, that doesn't seem real. That seems like...
Or why would it happen? Right.
Yeah,
why would
like zigzagging, making this weird pattern. It's like looking... It's like, that seems strange. But then when you see it on slow motion video, and we'll put some links in the show notes, it's fascinating watching these little creepy crawly flashes of electricity just scan through the sky. And then they connect, and then boom, that bolt goes through, and it's crazy.
It's like a great river, like a Mississippi or Ohio River, and watching all the tributaries to it. It looks like that in the sky, even though you don't see that because it's such low light intensity, and it's sort of a lot of times it's just pulsing, so your eyes don't really pick it up. That's what it looks like. So if you actually see a satellite view of the Earth, you see where the river's running. That's kind of what a negative lightning strike looks like. So it has that sort of randomness to it, like water running down a hill and finding the lowest path to wherever it's going to go. It's very similar to that. And sometimes the water channel will branch off because it sees a better place to go that way. And lightning, just the same thing. And so you have to think of the air as going from non-conductive to conductive, and it's sort of random. It's like Plinko. If you've ever watched
Well,
game
yeah,
shows, they play Plinko. It's just like that. Yeah.
and it's not always going in like you'd expect that the step leaders would always be going kind of down like towards their target, but then you watch
Nope.
some of them and they're making a 360 spin, like going back upwards slightly, and
Yeah.
then go. It's like, what are you doing, little step leader? Get back on track. Like, it's,
Right. Where are you
they've-
going?
yeah, like they have ADD or something. But
Yeah, and the video from the Midwest in the summertime or springtime, where they've had the thunderstorms are huge, huge. They go across states, and lightning discharges can actually run across states in the cloud, and it's just that sort of thing. Like, what is going on, and why is it continuing to create this continual line of flashes? And the satellites that we now have watching some of these lightning discharges are finding remarkable things that we never thought were possible. It's incredible.
yeah, so let's talk a little bit about some of these different types of lightning because they all have different implications on how much force is flowing through a wind turbine or a human if you're out walking your dog on the wrong time or whatever.
Right. Yeah.
But let's first talk about cloud to ground. So there's negative and there's positive, and what's the difference in the implications here?
So if you think of a cloud, I'm going to give you a very simplistic model because it's actually a little more complex than this. Usually the lower portion of the cloud is negatively charged and the upper portion is positively charged. And the most of the lightning strikes you will see, that negative charge is reaching out and traveling to ground. And you see this sort of spiky looking, heavily branched lightning flash. The first flash will look like it's all branchy, and then the subsequent, you'll see multiple flashes, bang, 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 bang. That's a negative discharge, negative cloud to ground strike. So it's got that pulsing, flashing light thing going on, and it has this sort of branchy look to it when it first strikes. Positive, which tends to be a little higher up in the cloud, discharge tends to be just one continuous reach out and hit the ground, and bammo, it just starts pouring energy into that channel. And there's very little branching in positive, and that has to do with the physics of electrons and atoms and all this stuff. But essentially, if you do see a positive charge, and that's the rare case, 5-10% are positive versus the 90-ish% that are negative. Yeah, they're just totally different. But for the most part, when you do see a lightning strike, in most places in the world, they're going to be a negative cloud to ground strike. Only in some weird circumstances, sometimes in the Midwest, sometimes on the coastlines where there's a storm rolling through the ocean, do you see a positive discharge.
Gotcha. And then obviously, I remember, I kind of remember the day, not the day, but I remember being told as a kid that no, lightning actually strikes upward. It's just like that's not true. Like it does strike from cloud to ground, and it also goes ground to cloud. It goes both directions. But
Yeah.
As far as the implications because we both seen some footage recently, which is intense of, the lightning originating from, wind turbines, especially because of just how they're the biggest feature on any given, piece of land. But what's the difference as far as the energy flowing through, turbine blade? Is it not dangerous because it reaches out from the turbine and then goes up, or is it still essentially the same implications for it?
It's the same implications. In terms of the energies involved, when the wind turbines reach out to the sky, and the first time I saw a discussion about this was, I think it was in Spain, and it may have been Gamesa or a university associated with Gamesa that was doing some research there, where there was a discharge somewhere else down on the edge of the storm. So it's basically there's a lightning discharge somewhere else, and then all of a sudden all these wind turbines light up and they start reaching out to the sky. Like, whoa, what is happening there? And then we've seen more recent video basically showing exactly the same thing. If you think about the way charge is up in the sky, and when you remove some of that charge, so if there's a lightning discharge 5 miles down the road, well, the storms are huge, and a change in one part of the storm affects the rest of the storm, and things that are tall, like wind turbines, all of a sudden can see this charge center right above them that wasn't there previously, and the wind turbines start to reach out and satisfy that and bring it to ground. And the energies in those things are not small either. So you have to think of a thunderstorm as not just being this pocket of charge, and once you dump it, it's gone. It's not that way. It's a very air is not a great conductor, and so different pockets of the thunderstorm will have different amounts of charge in them. And as things move electrically, it changes, and it changes very rapidly. And I think that's one of the things that I first saw from that paper in Spain was just the acknowledgement, like weird stuff's happening, and we're taking lightning strikes we didn't think we were taking on wind turbines, and we didn't understand why. Well, here's a good reason that the wind turbines are actually reaching up into the clouds and triggering strikes after a strike has already occurred somewhere else. That's
Yeah.
cool.
And is there any technology that that suppresses, like you hear of like lightning arresters, and
Yeah.
is there anything that can suppress that, or is it just it's just gonna happen?
That's a good question. You see advertised quite often, and I'm not a huge proponent of this, but I'm not a naysayer either. It's show me the data. But you'll
Yeah.
see these products where they say they're discharging the cloud by basically attracting static charge out of the cloud quietly and slowly, so the charge can't build up enough, and so it tends to be these kind of spiky things are stuck up in the sky, and maybe there's something to them. I'm not going to discount that, but can you stop it from happening? I don't think so. Obviously, people would disagree with me, and they're more than willing. I'm okay. Let's hear it, because the whole thing in a lightning protection sense is nobody wants to have lightning damage, and we all have our different ideas of how to prevent it. And my idea may work, may not work. Someone else's idea may work, may not work. The proof is in the pudding. Right? We have enough lightning strikes that happen in the world that we can test out these ideas and check them out. It'd be very similar to what we're going through, like with the COVID-19 right now. It's almost the same thing, except in a sort of medical sense, where we've got a myriad of possible cures or vaccines or serums or whatever they may be, and all of them have potential. And you have to sort of run them through clinical trials, be very objective about it, and say, is this working? Is this not working? Why? The same thing exists in any engineering field, and lightning protection is one of those where you really see a lot of things, but you're never sure if it's working or not. In my take, it ought to go through those same sort of experience. You need to prove that it's working, and maybe things that seem odd do work. And that's great, and because the goal is safer, more productive equipment and systems for, to advance society. That's what we're all looking for.
Yeah. So everyone, if you're out there listening, there's enough lightning to go around. We can all.
Yes.
Don't worry.
Don't
You
worry,
can
it's
all get
coming.
struck by lightning. You can all get your tests in.
Yeah, to a
Yeah.
neighborhood near you. Yes, it's coming.
Yeah, no, that's fair, and I'm sure it takes a lot of data to finally get to that point. I mean, I know there's a lot of companies out there collecting that data, but it seems like a lot of them are playing it pretty close to the vest, and that seems almost like a problem that's not really getting out into the public. Is that right?
Yeah, it's close to the vest, and there's a lot of reasons for it. I'm not sure any of them are extremely valid. It would be. I'm trying to think of a good example of what it'd be like. Like, let's just say it's a mousetrap. So everybody's got a better mousetrap, right? That's the old saying. You're just building a better mousetrap. Sure, you are building a better mousetrap, but there are. If I go to Walmart, God forbid that I go to a Walmart today, but if I went to a Walmart, I could probably find 10 different varieties of mousetrap, and some of them may work for my particular application, and some of them won't. That's what happens in lightning protection too. Everybody's got their own sort of mousetrap, and they're holding it as being the super effective against everything. I just don't buy into that. Not to say that conceptually that's not right, but there's never just one solution for everything. You need to take into consideration what part of the world you're in, how much lightning energy is there, are you on top of the mountain, or on the sea? There's a lot of variables that play into it, and people don't like sharing data also, which is the other thing. They don't like to be held up to studies. It makes it hard. It makes it hard to be good judges of it, and particularly in wind turbines, I think, because it's a ground-based thing. Aircraft people see themselves differently and want to work on airplanes and they don't want anything to do with sort of ground based. They live in slightly different worlds. Aircraft people are also very protective of technology because it can mean paycheck. On the ground turbine, on ground and wind turbine things, it's a little bit different because there's so many people who are involved with it, and they all have basic electrical lightning protection ideas and concepts, from sort of the Ben Franklin lightning rod all the way up to these static dissipation devices or triggering lightning strikes with lasers or something of that sort. Yeah. Is there, and I always go back to the same thing. It may work in your particular application. If you want it to spread it out, you better do the testing and show it. I know last week we talked about Applied Philosophy's SLPS device. They went out and tested it. They just went to the lab and said, hit it. Let's go see what it does. And they've also done, obviously, they've done some testing on wind turbines, and they've been able to show that it does work. And, is it going to be the best fix for a lot of Gamesa wind turbines? Yeah, it totally could be. But the proof's going to be in the pudding, and they're going to slowly implement it and find out. But that's the way engineering is, right? We just don't put a man on the moon. There's a lot of rocket launches and a lot of flying airplanes before we put a man on the moon. We're still in that stage with a lot of lightning protection.
Yeah, I know it's interesting. I've been looking up Tesla, and they actually have kind of like an open door policy with their patents. Like they've shared a lot of their patents on battery technology and stuff like that.
Yeah.
And I don't know, do you think that's something that could ever happen in this industry?
Did you watch that video with Elon Musk talking about just letting the patents go? Did you ever see that?
I've seen his whole Rogan podcast, and they might have mentioned it there. I know I'm aware of it, but I don't know if I've watched that in its entirety, that segment you're talking about.
His thought was, hey, we have this technology. If we hold it to ourselves, it's not going to become universal enough to actually make a difference.
Yeah.
And so, and he's right on. It's also a very Silicon Valley way of looking at patents, which is they have zero value besides paying some attorney to go on an expensive trip. It's paying for their vacations. It doesn't make a lot of sense in Silicon Valley because someone's going to rip you off. And by the time, so if I'm not saying this happens, but if Microsoft wanted to take your idea and use it, it'd be very hard to fight Microsoft and win. So from the Silicon Valley point of view, tends to be, we're just going to push out with this product. We're going to get 2 years out in front of everybody else, and they're going to have to acquire us. And that's okay. That's my patent. My patent is I have the company and I have the technology and I have the name. I am Uber. Now beat me, Microsoft. Right?
Yeah.
And that's the difference. And in the Lightning world, we still create, if you go online, it's easy to do. With Google Patents today, you can actually go check what the patents are in wind turbines, and it'll send you emails when they happen. But you can follow it. And in the wind turbine world, what you see is just patent. And I don't see a lot of those patents being implemented on the wind turbines, which is weird. Because if their idea is really good, they ought to be putting on the wind turbine. Creating patents for patent's sake, I don't sure helps the rest of the world. And particularly in the wind turbine field, where lightning is such a significant part of the downtime of a wind turbine and the damage and the expense of a wind turbine, are you helping the industry by doing that? Is that making you a market leader because you have a slightly better lightning protection design than somebody else? I doubt
Probably
it.
not, yeah.
Right, and it makes the industry appear sort of in its early stages. It's not. I mean, it's a very developed industry. It's and they're making wind turbines, 8, 10 megawatt wind turbines? Yeah, 12 megawatts, right? Yeah, hell yeah, 12. Yeah, so you have these big, huge machines, and we're still... We're way past that sort of techie Silicon Valley point. We need to be more ubiquitous. And if you want wind to be a real player long term, you got to just get it into society more often. And the Elon Musk approach and others, I think Apple had that opinion for a while. I'm not sure they do that anymore, but it was just like, here's the patents. You can go ahead and try and make this thing. Good luck to you. And we'll see you at the end. Yeah. It's probably a better play.
Yeah, if I had those patents, I'd be making my own iPhones every day in my garage.
Right.
Yeah, for sure.
Right. Or are you going to make a Tesla car? Like, maybe they are. And maybe they make their own competition. They probably will do that. there are a number, I just know, just because I'm in the industry, I know there's a lot of electric car programs outside of the sort of the normal automotive companies and Tesla. There's a lot of other ones that are going on simultaneously. And they're probably using the Tesla patents to advance their product. So Tesla will have competition, but the more choices you have and the more varieties of an electric car, the more likely that whole industry becomes accepted. And then they can take on, Tesla can take on a GM at that point because they have the market share. But until such time, Ford and GM and Chrysler and all the big automotive companies in the United States are just going to have their way.
Yeah, that's fair. So let's shift gears a little bit to testing. So we've talked about testing in other podcasts, but we were talking about a research paper that was kind of comparing scale models to full size. Yeah. And so what are some of the challenges there, and kind of tying in some of the different types of lightning, with all the different types, negative, positive, like all the different streamers, upward, downward. How can you, does the scale stuff work, and B, how can we reproduce all these different types of lightning?
Yeah. Okay. So there's two pieces of it. Are we adequately recreating the lightning event in the laboratory, and can we not use a 100-meter blade in the laboratory? Because what are you going to do with a 100-meter blade?
Exactly.
Right?
Yeah, for sure.
Right. You're not gonna right. At that point, you might as well just stick it out and see what happens out in real world and see what it does, because there's no facility that can handle it. So what tends to happen is you usually use a segment, basically the outer whatever couple of meters of a blade where the receptors are, or the thing you bring to the lightning lab. And the question always, and I agree with questioning this because it doesn't make sense. If I take the outer, say, just make it simple, the outer 10 meters, which is 30 odd feet. If I take the outer 10 meters of a wind turbine blade versus and leave off the other 90, does it change what happens at the tip? Yes. Oh yeah, it will. It totally will. Because the electric field intensity is going to be different, and the way it's going to distribute is going to be different. Yeah. And so you don't get exactly the same response from a segment as you do on a larger blade. And there's that paper that came out recently from the University of Nottingham's branch in Malaysia walks through that. Like they use COMSOL, which is a computational program, to compare the two. To see, because they were probably testing just the outer length of blade, and then they had the full blade to see if the laboratory results are going to match what would really happen in the real world. And the answer was no. They're off like roughly 15-20%. That's a significant difference if you're talking about whether a blade gets punctured or not, especially something that big. A puncture on a 80-meter blade, it's going to be problem. It's just a problem, and especially because those type of blades tend to be in remote places like the ocean. So getting the lightning test right is going to be a really important aspect. And so I think the same. I'll give it the similar example because I think this is exactly the same thing exists for airplanes, which is what we call model tests. So on an aircraft, early on in the design process, you can determine where lightning may attach to an airplane by creating a model. And so let's just say we got an Airbus A380, which is a gigantic airplane, and I got to shrink that down to, I don't know, say 1/100th of the size. Mm-hmm. So I can get it into a place where I can get it into the lab, in the lightning lab, and then do lightning strikes on it. So the electrical event is all scale. It's 1-to-1 what's happened in the outside world, but the airplane is roughly 1/100th of the size. Are you getting the same result?
Yeah.
You won't. You won't. The computational people all the time will poke at us and say, that model test is, they'll say the model test is garbage. Okay, it's not garbage. It's telling us a lot about where lightning is going to attach. But I can push back the same thing computationally. Like, well, computational having it's just a guess too, right? Where we put the model, it gets pushed out the other end. Is it right either? And the same thing exists in wind turbines. And ultimately in all of this, the answer is you're going to put it out in the field and you're going to find out, and then what you should be doing is learning from what your experience is in the field. And like we just talked about with patents, we need to get that information back into the hands of engineers so they can make the next generation better across the board, across the board.
So what would be your suggestion then? So if we know there's some limitations to testing,
Yep.
and there's probably no perfect solution.
No.
Where do you think we go?
That's a really good question. Man, you're full of good questions today.
Yeah, stumped him.
Here's what my gut says. We're getting good computationally, and we have more horsepower. I was just talking to my son about the new Mac Pro computer and how many processors it have. Like, wow, there's a lot of horsepower in a device that can sit underneath your desk today. That would have taken a room full of computational power. I think we're going to get to the point that we're going to be able to simulate a lot of lightning events on a computer. And now, can we simulate the fine details yet? No. That's where the problem lies. We can't simulate fine details, and a lot of the lightning punctures are fine detail problems. But we're getting closer and closer and closer. So the push is going to be in the computational side, because I don't have to test a big blade. But at the same token, I got to be watching when I do put that blade into service. I got to be watching what's happening and putting that back into the model. The worst case is I do a model, I say it's good, I push the blade out the door, and then I never go back and look at it. Well, that's not engineering. That's Vegas, right? You're just you're pulling the handle on the slot machine, and yeah, you may get a payout, you may not. That's not engineering. The feedback is where engineering occurs, and that's, in my opinion, that's the place where we're probably the weakest, because we have a lot of computational power, but I'm not sure the engineers are in touch always with what's happening in the field.
Well, so is there any? Do you have to test a blade with lightning originating coming out through it and then back into it, like you would, from an upward strike to a downward strike? Like, do you have to do that, or is that not really relevant in testing?
Well, you're sort of doing it because of polarity. So in one aspect, the blade would be negatively charged, another tested blade's positively charged. And you see different, think of it as you're creating this cloud of charge above the blade in the lab. And this cloud of charge in the lab is basically typically a metal slab of some sort. Or better yet, in the way that we do it on airplanes, and they started doing it on blades more recently, is they actually take the blade in a crane and lift it off the floor. It's suspended over a flat metal sheet on the floor, and then you energize the blade and let it arc over the floor. That seems to be a lot more realistic than some of the things I've seen in some recent papers, where they have an electrode above, a pointy electrode above a blade, a couple meter blade that's sitting above the ground. That configuration doesn't make any sense to me. What makes sense to me is you take the blade, you energize the blade, because lightning is not running into the blade. The blade's actually reach out into space. So you positively charge a blade, then you negatively charge a blade, and you see what it does. One of the things I know from doing aircraft tests and radome tests is, as you charge a blade the first time in the test, there's charge left on the blade. So the next test you're going to do is going to have a slightly different result, because there's charge already on the plastic, the fiberglass structure of the blade, and it had no place to go from the first test you did. So the second test is going to give you sometimes a slightly different result, and the third test will be different. If you change polarities, it'll wipe that out and restart. In the real world, and if you think about it in the real world, as the blade kind of spins, it's kind of like coming up to the cloud, sees the cloud, charges up, goes away, comes back up, charges up, goes away. So by the time the lightning event does occur, there's a lot of charge on the blade, and things are not as electrically pure as we see in a model or in a test.
Gotcha. Well, that's all very complex.
It's totally complex, right? And that's
like something we should be able to solve quickly, but it just isn't. And it's
we haven't done it. We haven't done it. You can there are plenty of drone companies like SkySpecs that are out there all the time looking to repair blades and inspect blades, because they're getting punctured all the time. So all the testing we did and all the analysis we did hasn't eliminated the problem. And hopefully, the point of a company like SkySpecs is that they can start feeding the information back to the engineers directly, and the engineers can then incorporate that in their next design and start eliminating some of these things. That's the goal, right? The goal is to keep these wind turbines, and if we to keep the wind turbines moving and operating all the time. And as an industry, we need to get to that point. We got to get to that point. It'd be like buying a car that only ran 200 miles, and then you had to go in for a full tune-up. That's no fun, right? You should, once a year, give a quick tune-up and get the car on the road again. You just can't have random events knocking the turbine out of service. That's not where we should be today.
Yeah, and then, I mean, are there other issues as far as, I mean, why can't we have a little mini wind turbine farm that is just used for testing? Is it just too cost prohibitive to do that? I mean, why does it have to be done inside of a warehouse, inside of a lightning lab?
Simplicity,
Yeah.
speed. They always test the wind turbines. So if they have a new blade design or new generator, they will actually make a prototype and put it out, install it. They may put on a new tower and install it and run it and check it out. It'd be like a new car or a new airplane. They're going to go through a series of tests, and one of those is just a real world test, but they tend to build one of them.
Yeah.
And then if they get struck, and I've seen some reports where the development blade slash wind turbine has gotten struck just by happenstance, and they use that as justification of why the lightning protection system works great. Now, that's just, to me, that's not really engineering. That's just anecdotal information. But should we be able to do it? I think let's go back to the computational thing. We shouldn't need to have a field full of physical wind turbines. We should be able to do it computationally. We have the horsepower to do it. Just do we have the willpower to grind it out and get better models so we can do it?
Yeah, that makes sense. And is this something that, I mean, as engineering students finish their degrees, is this something where there's enough, academic power coming up through the pipeline? I mean, is this something people want to study to advance this? Or does this have to be funded by private companies? I mean, does a big company like Siemens Gamesa have to kind of push to get these computational models built?
Both. Now, I will give you the difference between the United States and the UK, for example. And maybe it's just the different way that engineering programs are established. But in the United States, there's not, where's the high voltage program? I think Mississippi State still has a high voltage generator lab, a lightning lab, and a high voltage lab where undergrad students can get some exposure to it. But I don't know of many others. If there are a bunch, I don't know of them all. And Mississippi State, I believe that's the one that comes to mind. I think it's Mississippi State. In the UK, the University of Manchester has a huge high voltage lab that has undergrad students and graduate students in it all the time. Same thing for Cardiff. They have a lightning lab. It's sort of funded by Airbus, but they have a lightning lab there where undergrad students and graduate students can get hands-on exposure to the lightning world. In the U.S., it's just not the same. You just don't have those facilities in terms of, and even in per capita, just Manchester and Cardiff, having those two places. In the UK, you would have to have 10 of those in the United States at least.
Yeah.
And we just don't. And so what happens in the States is that you get hired on at a company and you work with the previous lightning engineer, and you learn as much as they're willing to dole out, and then you have to just skedaddle and work hard and put your nose to the grindstone and learn as much as you can and go to watch some Tom Warner videos and read all the things out of Gainesville, Florida on lightning protection. You listen to someone like Andy Plummer, who has a ton of lightning knowledge, just rolling around in his head the whole time. It's sort of old school, and it's not sort of old school. It is old school. It's just passed down generation to generation, and I'm not sure that's a great thing for the United States. It needs to be more of a UK model where undergrad students are getting some exposure to this stuff, and we would have a lot less, in my opinion, we'd have a lot less lightning issues. We have a lot of kids going through school right now that know a lot about computers, and that's great, but that has nothing to do with lightning protection in a sense.
So you're
And
saying you're saying Snapchat doesn't carry over to the lightning protection world?
No, and think of it in sort of baseball or sports. There's sort of a minor league system which you sort of earn your keep in a sense that if you do well enough, you move to the next level. Well, it's just like that in engineering still, but you're just learning how. It'd be like learning how to play baseball the first time when you reach low level A baseball. That's just it's just crazy. You should come in with some skills. You don't have skills as an engineer. You have some fundamental skills, but you don't have any specific skills specific to lightning. Because a lot of the lightning issues and having to do with the power distribution network in the United States have been solved years ago. But the airplane one hasn't always been solved, and the wind turbine one clearly hasn't been solved. And there's numerous other ones that haven't been solved either. So our unwillingness to or our at the time thinking we're not going to have any more lightning issues and shut it all down back in the 1980s was short-sighted, and it's put the United States, in my opinion, behind the curve a little bit. Some of the best papers on lightning protection come out of Europe. Almost all of them do. There's some good ones in the United States, and there's some really good ones in Japan right now, some brilliant ones coming out of Japan. And China's invested a lot in some lightning protection and high voltage labs where they have a bunch of students learning. So, the United States is not the leader in lightning protection right now. I would not say that.
Gotcha. I wonder, maybe as a rite of passage, in the police academy, if you're going to carry mace, you have to be maced yourself. So I feel like in the lightning industry, if you're going to work in this field, you probably just need to run out into a storm, into an open field, and maybe wave a broomstick around and take one for the team, so you really understand lightning.
Well, I think no,
it's only fair.
I wouldn't say that this is factual, okay, but it sounded like when General Electric had their lightning lab down in Pittsfield, Massachusetts, that they had some of those initiation things were happening. Not that they would shock somebody, but they, I don't want to get into it too deep, but it sounds like there was some initiation going on there, so you got to earn your keep. But yeah, I think that as time has changed and we've gotten more and we've gotten more desk oriented and less out in the lab oriented, we've lost a lot. I think being out in the lab and doing those experiments and getting the physical world put into your head pays off dividends later on.
Yeah, gotcha. Well, obviously the United States can't be the leader in everything, and if there's good research coming out and it comes from Europe, so be it. I mean, that's a good thing for the industry, but yeah, it does seem like there's a disconnect. Like maybe there's, like you said, not the pipeline that there should be. Yeah. With all the higher education here in the U.S. So.
Yeah, that's true.
Well, yeah. Well, Alan, great episode today. Appreciate your insight as per usual.
Yeah, thanks, Dan. I appreciate you, and you've been doing a great job on these podcasts.
Well, just trying to keep up, and maybe I will. It's stormy out tonight. Maybe I'll run out there and learn and learn a thing or two. There's some good buildings I can scale. Just maybe hang out with the lightning rod for a little bit, and see what I learn. Maybe come back with a big scar or something as it goes in and out. We'll see.
I'd rather have you watch some Tom Warner videos.
If I'm here next week, then I survived. You'll all know. But yeah, so thank you for listening in. Obviously, this is the Struck Podcast, and check us out on Spotify, iTunes, anywhere you listen to podcasts. Also on YouTube, where we have full-length videos and short clips. So if you're looking for some little topic, you're an engineer, or you're just really interested in lightning and renewable energy, we have lots of little quick clips that you can just grab and go 3, 5, 10 minutes on YouTube. And so whatever way you want to digest our content, we've got something for you. So obviously, subscribe to the show, share it with a friend, check us out on Twitter, LinkedIn, Facebook, even Instagram, and we will catch you here next week on the UPTIME podcast.